Electron configurations of ions. So ions form when electrons are gained or lost. An anion, you're gaining electrons, and cations, you're losing them. So the main group cations, we're losing electrons, and so if we look at something like the aluminum atom and the aluminum ion, well, 3+, we need to take off 3 electrons. Which ones do we take off? The main group elements make sense. You take off in reverse order of filling, right? So this 3p was the last one we added. You get rid of that one. Okay, now I need 2 more electrons to get rid of. The 3s were the next to the last ones, and so you take those off, and you end up with this electron configuration. Question?
You might want to change the helium converter.
Yeah. That's... Wow, that is the book's mistake. Thank you. That is neon. So neon, 2s2, 2p3, in the atom of aluminum, we had 3s2, and we had 1 electron over here in the 3p. Oh, no, you know what? That's actually correct. This actually is, it's helium. If we were doing the atom, it would be neon. It would be neon plus this business. So that was okay. So we're going to take these electrons off, and then we're left with this, which has the same electron configuration as neon. Any questions? So this is the same electron configuration as neon. Transition metals, not as simple. You're going to remove the valence electrons first, even though those may not have been the last ones added. Those are the ones in the outermost shell, and those are the ones that are going to get removed. So if we look at iron, here's the electron configuration for iron. There are 2 valence electrons. Most of the transition metals have 2 valence electrons. It's those guys right there. The 3d electrons were added after. Those orbitals fill after the 4s, but they do not get removed first. The valence electrons are removed first. And then you start going into the core electrons. So the Fe2+ ion, we've lost these guys. And next, if we're making Fe3+, we're going to lose one of these 3d electrons. So we're going to have this situation. So we end up with no 4s electrons, and we get the 3d subshell half full. Any questions? The arrangement of electrons determines whether something is magnetic or not. So an atom or ion is paramagnetic if it has unpaired electrons. Paramagnetic ions or atoms will be attracted to a magnetic field. Some metals are magnetic, others are not, right? Just because it's metal doesn't mean it's magnetic. Now the material that my table here is made out of is magnetic. This magnetic stylus sticks to it very nicely. Stainless steel refrigerators, not magnetic, right? You can't stick magnets and hang up papers on a stainless steel refrigerator. It doesn't work because stainless steel is not magnetic. The reason these are magnetic is because that unpaired electron generates a magnetic field because of its spin, and that magnetic field is attracted to the magnet. Diamagnetic, all the electrons are paired, and these are actually slightly repelled by a magnetic field. But they will not interact with the magnetic field significantly. So we have to remember paramagnetic, diamagnetic. I'm going to look at a couple of examples here. So write the electron configuration and the orbital diagram for each ion. Predict whether each will be paramagnetic or diamagnetic. And we're just going to look at, well, scratch that. So cobalt. Cobalt 2+. Well, let's first look at cobalt itself. And we can look at just the valence cell for cobalt. So it's going to be argon. And what's next in the electron configuration? 4s2. And what's next? That's the 3D filling up, right? 3d7. Are we okay with that? That's the electron configuration. If we look at this orbital diagram, we've got the 4s here, and that has 2 electrons in it. And then we've got the 3d, and the 7 electrons would fill this 1, 2, 3, 4, 5, 6, 7. Those are the atoms. Those are the configurations for the atom, cobalt. We're looking at the ion. Which of these electrons is lost when it becomes an ion? The valence electrons. So it's these two guys. So these guys are bye-bye. Now we have the electron configuration for cobalt 2+ ion. And so over here in the orbital diagram, it's these two guys that disappear. I'm going to get rid of them. Gonzo. So to identify whether this is paramagnetic or diamagnetic, we look at the orbital diagram and see, are there unpaired electrons? Yes, there are. Is this paramagnetic or diamagnetic? This is a hard association. I struggle with this one. I have to think about it. Because paramagnetic sounds like pairs, right? And you think, oh, paramagnetic, they're all paired up. No, it's the opposite of that. So what works for me is diamagnetic. Okay, so di is 2, right? There's 2 electrons in a pair. Diamagnetic, they're paired up. Paramagnetic, not. So this has unpaired electrons. This is paramagnetic. And that's one you kind of have to work out for yourself. I would have chosen different words, but as I've mentioned before, they didn't consult me. Paramagnetic. Any questions about that one? How about the nitride ion? Well, they want us to write electron configurations. So nitrogen's small enough. Let's just write the whole business. 1s2, 2s2, 2p3. All right? For the nitrogen atom, that's not even close to a square. So if we look at the orbital diagram, there's 7 electrons, and so they'll go in 1, 2, 3, 4, 5, 6, 7. Nitrogen, the element, is it paramagnetic or diamagnetic? Paramagnetic. It has unpaired electrons. Now let's make the ion. When nitrogen atom becomes nitride ion, does it gain or lose electrons? It gains electrons. It's easiest to look at the orbital diagram. So 3 minus means that it gained 3 electrons. They're going to go in here. To adjust the electron configuration, we have to change that 3 to a 6. Now we have the information for the ion. Is the ion diamagnetic or paramagnetic? Are they all paired up? They're all paired up. Diamagnetic. Any questions? Got to look at the orbital diagram. We'll see if they're paired or not. Once you get good at it, you can look at the electron configuration, but you guys are just getting started on this, and I find that iffy, so I wouldn't recommend that. Trends in ionic radius. So we looked at atomic radius, but let's look at the ions. So cations are much smaller than neutral atoms, and them being smaller does make sense because you form a cation by losing electrons, right? And you're generally losing the valence electrons, so you're actually dropping down a whole shell. So it makes sense that they're smaller. We've lost the outermost electrons. We still have the same charge on the nucleus, and so the effective nuclear charge is increasing. And we see very distinct differences. So it's too small for me to read. Lithium, the atom, lithium, the ion. Huge difference. Lose 1 electron, the thing just shrinks up to almost nothing. The difference is not as great for a larger atom, but here rubidium to rubidium plus, again, gets smaller. So cations are always smaller than the atoms. Anions are bigger. The anion is larger, we're gaining electrons. And it's not that we're gaining electrons in a new level. The valence electrons are still in the same level, but we've added electrons and we haven't changed the nucleus. So the effective nuclear charge is going down, which means that the electrons that are there are not held as tightly. And so we see from, what is that, tellurium? Let's look at iodine. So the iodine atom, 133. The iodide ion, 216. Those things are way too small.
What's this effective nuclear charge for the ion? Is it -1?
The effective nuclear charge of the ion. It's a little harder to calculate, but we have more electrons and we have the same number of protons, and so it goes down. It's not as easy as just subtracting, but it does go down. So trends in ionic radius. When we talk about isoelectronic ions, iso is a prefix that means the same. And so isoelectronic, they have the same number of electrons. They are not the same atom, but they have the same number of electrons. So they have the same electron configuration. If we look at these guys, sulfide, chloride, potassium, and calcium, these guys all have the same electron configuration as argon. They all have 18 electrons. But calcium has 20 protons, sulfur only has 16 protons. So the effective nuclear charge for sulfur is less than for calcium. Calcium has a radius of 99 picometers. Sulfide is 184, almost twice as much. And it's all because of the effective nuclear charge, the charge on the nucleus. Because the electrons, same number of electrons occupying the same orbitals. The only difference is the nucleus. So let's look at these. Choose the larger atom or ion from each pair. Potassium atom or potassium ion, which is larger? Well, let's think about it. When the potassium atom becomes an ion, does it gain or lose electrons? It loses an electron. And so that's good enough right there. Losing an electron, it should get smaller, and it does. So the potassium atom is larger. Cations get smaller. Fluorine atom or fluorine ion? Fluoride ion. Well, the fluoride is an ion because it got an extra electron. That affects the nuclear charge, the effective nuclear charge. The anion is larger. Anions are always larger than their corresponding atom. Cations are always smaller. Now this one requires a little more thinking. Calcium ion or chloride ion? Well, we look at the periodic table. Calcium ion and chloride ion both have 18 electrons. The same electron configuration as argon. So then how do we decide which one's larger, which one's smaller? How many protons do they have? Which one has more protons, calcium or chlorine? Calcium has more protons. More protons in the nucleus is going to have a larger attraction for the electrons. It's going to pull them in tighter. So which one's bigger? Chloride's bigger. Same number of electrons. You might think that calcium would be bigger because it has more protons. It's actually smaller because it has more protons. The charge, the attraction is greater, everything pulls in. Any questions? There's trends in ionization energy. Well, what is ionization energy? It's a long two words, and so we often call it IE. The energy needed to remove an electron from an atom or an ion in the gas state is how it's defined. This is always a positive number because it requires energy to be put into the atom. So from the atom's point of view, this is positive. You're going to have to pay me for that electron, basically. You're going to have to do something for me to give up that electron. So if we look at a metal, that's a G, some metal in the gas state, if you put in the first ionization energy, you can pull one electron off. If you put another bunch of energy in on the Mg, it's just playing with my mind, this metal ion, the second ionization energy is pulling off the second electron. And then there's a third and a fourth and a fifth. So the first ionization energy, removing an electron from a neutral atom. Second is removing it from a +1. Third would be removing it from a +2. What we see is that the first ionization energy decreases as you go down a group. So if you look at the noble gases, as you go down the group, it becomes easier to remove an electron. Well, the electrons are farther from the nucleus. You're taking a valence electron off, one on the outside. And here I talk about family size. So I've got 6 kids. I have a friend who has 1 child. And, you just can't keep track of 6 kids the way you can keep track of 1 kid. 1 kid, you can keep your eye on them. This is one of the reasons I do not go to the fair, right? It's a great place to lose children, which some days is appealing, but overall I don't want to lose my children. You can't keep track of them. And so you think about xenon. Xenon has 54 protons and 54 electrons. So if you had a woman with 54 children compared to a woman with 2 children, whose children would be easier to kidnap? This is not a politically correct analogy. Well, it'd be so much easier to take one of Xenon's children. She might not even notice, at least for a while, right? As these get larger, it becomes easier to remove one of the outer electrons. They're farther from the nucleus. The force of the attraction is less. Those valence electrons are farther away. As you go across a period, though, so this period 2 going from lithium to neon, now look, there's jaggedness in here. It's not a definite absolute trend, but it's a general trend. As you go across, the ionization energy increases. Well, what happens to the size as you go across a period? The atom gets smaller, right? Because the effective nuclear charge is increasing. This mom is more aware, she's stronger because she's got more protons. And so she's like keeping track, and her children are closer. The electrons are closer, they're harder to take away. The other way I think of it is you look at something like, this would be fluorine, right? Fluorine is 1 electron short of a noble gas electron configuration. Fluorine is wanting to gain an electron. He's really going to be unhappy about losing an electron. And then look at sodium. Sodium down here. I'm sorry, this is lithium. I want to look at lithium. So lithium, if lithium loses an electron, he looks like a noble gas, right? So lithium is probably going to go along with this idea of losing an electron pretty easily, right? But as you go across, it becomes harder and harder. Here's the general trends in first ionization energy. We see as we're going down, it decreases. As we go across, it increases. On basis of periodic trends, identify which one has the higher first ionization energy. And they put in here, if possible. Because sometimes just from position on the periodic table, you can't tell. So tin or iodine. Well, tin and iodine are in the same row, right? So what's the trend? As you go across a period, it becomes easier or harder to remove an electron? Harder. Iodine would really like to gain an electron. He's going to be not real happy about losing one. So the higher ionization energy in the period is the one to the right. Calcium or strontium? Calcium and strontium are the same group, right? Strontium is larger than calcium because the valence electrons for strontium are in n equals 5. Calcium's n equals 4. Electrons that are farther away are easier to remove. So which one has the higher ionization energy? Somebody say it. Calcium, thank you. Carbon or phosphorus? Oh, that's a tough one. There's calcium, there's phosphorus. Here we have a situation of opposing trends. So as we go across, ionization energy becomes larger. As we go down, go down, it gets lower. Opposing trends. Well, it says if possible. So the safest answer here would be it's not possible. Can't tell. What if you were forced to choose? Let's look at this graph. As we're going across, right, they're getting larger. As we're going down, they're getting smaller. But which trend is steeper? Going across this way or this way? This is a steeper trend than this one. Do you see that? So in this situation, going across the period is more significant than going down in a group. So if I was forced to choose on this one, I would pick the phosphorus as having the higher. But I would consider that not a good exam question. It's really not enough information. How about fluorine or sulfur? So again, these are related diagonally in the periodic table, fluorine and sulfur. But here the trends are reinforcing each other. As we go across, ionization energy increases. As we go down, it decreases. And so these trends are reinforcing each other. Which one has a higher ionization energy? The fluorine. Any questions? I'm pretty much guaranteed there'll be one of those on the next exam. Exceptions. We noticed there was some jaggedness in those trends. We see an exception between groups 2A and 3A. Boron has a smaller ionization energy than beryllium. What's happening is that boron is losing a 2p electron, whereas beryllium is losing a 2s electron. The 2p electrons are easier to lose than the 2s electrons. And it says draw orbital diagrams. That's a reminder to myself of what I'm supposed to do in that blank spot. Well, boron. Boron has, we'll just look at the valence shell, 2s2, 2p1. So here's 2s, and here's 2p, and this is for boron. We got 2 electrons here and 1 electron there. For beryllium, beryllium's orbitals are not larger. And that's not a 1, that's a 2. So beryllium has 2 valence electrons, and they're in here. This is less stable in energy than this 2s electron. The order of filling tells us that, for one thing. As you go from 2s to 2p, the 2p is a higher energy orbital. That makes it less stable. So it's easier to remove this one than it is to remove that one. But that's not what our general trend told us. So there's some glitches in the trend. Any questions? We have another glitch between 5A and 6A. So here's nitrogen. Here's its orbital diagram. Here's oxygen, its orbital diagram. If we're removing an electron from nitrogen and from oxygen, we're removing a 2p electron from both of them. It should be the same, except maybe with the effective nuclear charge, we might expect that oxygen would be a little harder. But there's an extra stability when you have orbitals that either, or subshells that are either half full or completely full. And so nitrogen here is half full. It's like a bonus situation. Oxygen does not have half full. And so we're removing 1 electron. When we do that, we get half full. And so that's actually easier than for the nitrogen, which is opposite of what we expect. I'm not going to expect you to be on top of all these little exceptions, but I just want to tell you they are there, and this is why. There is a reason. What if you're removing another electron? Well, that requires more energy than the first one, because the effective nuclear charge has increased now, and so it's going to be harder and harder. The more electrons you remove, each one is going to require more energy. Because what happens when you form a cation to the size? Does it get bigger or smaller? It gets smaller. It gets quite a bit smaller. And so now those electrons that you're trying to remove are even closer. Think of the mom, okay? So somebody kidnapped one of my kids. I'm going to keep a closer eye on the rest of them, right? And so it's going to be a lot harder to snatch a second one. I don't know if that works for you or not, but that's a peek into how my mind works. It's kind of scary. So we get a large, we see there's a large increase when the first core electron is removed. Removing valence electrons, the energy increases, but once you start removing core electrons, it becomes a lot harder. So what we see here, sodium has 1 valence electron. Removing that one is 496 kilojoules per mole. The next one is 4,560. That's a lot bigger. What the heck? Well, that's because now we're removing a core electrons. Things are getting personal now. It's like, no, don't mess with those core electrons. The valence electrons, but the core electrons, you leave those alone. And then this one, 6,910. For magnesium, magnesium has 2 valence electrons. So the first one is 738, The second one is 1450. The third one is the huge jump. Because after you got rid of the 2 valence electrons, we see this huge jump when you start taking off core electrons. So you can actually predict things about these elements just based on their ionization energies. Because what we see is this huge leap every time we get into the core electrons. Aluminum has 3 valence electrons. Taking the 4th one off is a huge jump. Chlorine. Chlorine has 7 valence electrons, and so you can take off all 7 before you get a leap. But for sulfur, it has 6, and the 7th one is this big jump.